So look at this. So it goes faster and faster. Doesn't need that much time anymore. Good. So let me just double check that it's going to display well. Oh yeah, one more thing I need. This guy.
Apparently the this efficiency of streaming is...
It's getting better.
It has a direct relation to the number of students present.
Yeah, thank you. Get be. Yeah, don't make it too dark. Looks good there, but yeah, but this is too much lightning. I see that. How it appears in the YouTube. Yeah, but
The sound quality is good.
So how is the screen? It's like perfect.
Yeah. So can you stand up so that we can adjust the height?
Sure.
Yes, it's good. Maybe a little bit down.
Down? You sure? Because if it cuts my head, you know, it looks kind of funny.
Yeah.
So.
You're right. Okay, but I believe I have to make it darker because right.
Yeah, you're right. It's way too much lightning, and it's not clearly visible there either.
So we just need to.
Should I stand up?
No, it's just the screen. We have to adjust it a little. Maybe a little bit to the left. Yes, nice. Everything's fine.
Is it the other I'm a little weak here, or how come I'm not able to log into my channel?
No, I'm connected to the journal.
So you connected to the other room? Okay. Now this is super slow. There. Okay, this is live. Okay, it looks pretty good. Now what do you say?
Yep.
Good.
You have 5 more minutes.
Yeah, I do. I'm gonna just sit down, wait. Sit and wait. Okay, so we're gonna close at 5:35. 5:35.
So 5:40.
Yeah, 5:40. 5:40, and then I need to collect my stuff, rush my office, and have this question and answer session. Yeah. Good. Almost good to go. You know, look at this thing that is here, still here.
It's a sign.
Yeah, it's a sign, you know. Now I'm gonna put it in my bag. Because I don't need this, I can put this off. I can put this off too.
Oh, Aki.
Is it moving?
Yes, you have moved it.
Is it?
Let me check.
No, it looks good.
No, like, yeah, it's right now it looks good.
It's okay.
Okay.
Okay, 5:35.
5:35. So see you.
See ya.
And can you assign another YouTube officer or something? Because
Yeah,
last
I know,
week
I know.
somebody else kind of.
Yeah, there was a problem. I think
Yeah.
the screen was black for a
Yeah.
while, and I was unable to notice. Yep.
Okay. See you.
See ya. Te olette niinku takas täydellä miehityksellä. Yksi puuttuu. Joo, okei, joo. Mikä se oli viime viikolla, kun oli niin vähän opiskelijoita muutenkin?
Me seurattiin mereltä.
Mereltä? No joo, oliko se joku opiskelijaristeily vai? Ihan vaan risteily, okei. No, oliko se niinku helpompaa siellä risteilyllä seurata tätä kuin tässä näin? Kumpi oli viihdyttävämpää?
No varmaan keilu edestakassa.
Joo.
Ilta vähän painollisia.
Okei, joo. Että oli kova merenkäynti. Joo.
Siinä vaiheessa oltiin jo tulossa takaisinpäin.
Niin kävittekö Ruotsissa vai Tallinnassa vai missä?
Turusta kohteeseen
Okei, joo.
vuorokauden.
Ai jaa, niin että yhdessä vuorokaudessa takaisin.
Niin.
No mikä se niinku sitten käytäntönä, ideana?
Taas se risteily. Se oli se risteily.
Aha, no niin, mikäs?
Ei ole pari tanssia vielä.
Joo.
Ensin
Joo.
pitää pelaa nestiä.
Selvä.
Tuffa hanajuoma.
Niin oliko se kaikki ruoat semmoisia, että niitä olin, että saa niinku syödä niin paljon ja juoda niin paljon kuin haluaa? Joo, okei. Mutta ette päässyt käymään Tukholmassa. Mutta eikö se ole nyt niin, että nyt ei ole tarvettakaan käydä Tukholmassa, kun nuuskaa saa, tai sitä vastaavaa saa Suomestakin? Ei tarvitse mennä enää Ruotsin puolelle.
Niin ja laivasta.
Ai niin, on laivastakin vissiin saa.
Siitä laivasta kyllä saa, mutta se on vaan vähän, niissä on rajoitukset on aika tiukkoja. Ja sitten käytännössä kun tulisi auto, niin saisi kummin tuotua.
Okei. Mutta eikö sit saa tuoda niin paljon kuin jaksaa kantaa? Niin kuin kilomäärällä? Jaha, okei. Joo. Selvä. Oh, okei. 30 something seconds. Ai hakemaan nuuskaa. Joo. Okay, guys, in 10 seconds we're gonna go. 10 seconds. In 5. Okay. Respect. Good thing. So, look at this. So, it's lecture number 6. So, this is the last lecture we're going to learn new matters for midterm exam. And after today's lecture, what follows is one more lecture on next week, Monday. And that's going to be simply summarizing what is that I'm expecting you to know when you're entering the midterm exam. Also, what is that I'm, kind of like what are my hints to you? What are the ways you can prepare yourself to midterm exam? And I understood that Alfonson's tutorial last week, guided tutorial, was something very useful to you guys. So you learn how to use symbolic math tools in MATLAB. And if you are not familiar with that, I think you should better take a look at the recordings that is available in a Moodle database. So, but again, this is the last lecture before we can actually wrap up things. So the last lecture is equations of motion. So what will happen today is that we're gonna express all the forces in a way that we can start solving the responses, dynamic responses, and that's what going to be the challenge of today's lecture. There's quite a few things to discuss, and there is something that is mathematically a little bit involving, and that is related to use of Lagrange multipliers. I think this is something that you might be already familiar with, and we're going to make use of that technique when we're taking constraints into account. Okay, so without further ado, let's summarize what we discussed a week ago. So a week ago, we actually were able to express externally applied forces, which can be expressed as shown here, which is a mass multiplied by acceleration, and can be treated like any other force because of the D'Alembert. D'Alembert figure out that there is same rules applies to inertial forces that applies to externally applied forces. So what we did for these forces is that we converted this force to be expressed using generalized coordinates. Now, what's the big problem in the form that the equation, or let's say the inertial forces are expressed like this? The big problem is that in a form like this, if you look at carefully this equation, it includes r dot dot, which is coming from the r, and r coming from, that there is a r that you need to differentiate to get r dot, and then r dot dot. So this was a acceleration, this is a velocity, and this is a position. Now, in a position vector, when it is expressed like it is shown here, this one consists of two components that are rx and ry, that are components with respect to global coordinate axis. And that's not okay, so that's not cool. We need more than that, because we would like to express this force with respect to generalized coordinates. And the generalized coordinates for the one single body are rx, which is a projection along the global x coordinate axis, ry, which is the same for y coordinate axis, and angle theta. So obviously the missing component here is an angle theta. And what we need to do to convert this force to take from 2 component to 3 component was something that was called a mapping. We're going to introduce the mapping with help of virtual work. And the virtual work is like any work, except when the work takes place, we are assuming time to be frozen. The time is not running. And that's something that is very important for us, because that introduces us relation between the global coordinates, let me write it like this, and generalized coordinates. And something that relates these two matters are partial differentiation of q with respect, r with respect to q. And that's our mapping matrix. This one here, so let me write it in a more clear way, like this. This matrix here consists of 2 rows, 3 columns. So it's doing the mapping, what we're looking for, exactly the way that we are after here. Okay, so how that happens in reality. In reality, when you take a look at the details, so it's mathematically very, very bad. So it needs a lot of matrix operation, a lot of mathematics back and forth. But if you take a look at the big picture, it's not that bad. It's not that bad at all. So eventually, so it's kind of what we are after here is that we wanted to make a use of the fact that this force here, again, the inertial force is with respect to this delta r. And the delta r, this is where we exactly can introduce the mapping what we are after. So the mapping is this one, like I just explained in my previous slide. So delta r, delta q. So these are the linearized form, so it applies in a certain configuration only. Once the configuration changes, we have to update this matrix. Okay? So now, when you look at the details, this is how the acceleration can be expressed when you explicitly mention the generalized coordinates, which are acceleration here and velocity here. When you're making use of the mapping matrix, when you substitute all in to this generalized generalized inertial forces, this is how it's going to read, and it consists of 2 components. The one that is linearly related to accelerations, so it's a mass matrix multiplied by acceleration of generalized coordinates, that in turn consists of translation and rotation, this component like it is shown here, and then something that is called quadratic velocity vector. Not a big surprise, because if you look at the how is a velocity here, so velocity where we look, this one here, this guy here, it consists of two components, the one that is linearly related to accelerations and the one that is quadratically related to velocities. Where these initially came from? This came from the kinematics that we selected to be used, and this is a kinematics we select to be used. If you select some other kinematics, then you might have a different form of your equation of motion, but we want to make a use of this particular definition. Okay, is this the only way to make it happen? No, like I said, there are many, many other ways to make it happen, but this is a fairly straightforward as it is based on global coordinates. And this form where we have these generalized coordinates like it is shown here, this is called as a global coordinates, even though they are describing the body reference coordinate system with respect to global coordinate system. Alternatives that you might have seen in robotics are relative coordinates. And that's a conceptually different story, because then what we're looking at is that we're looking the body is connected together via different kind of joints. Like if there would be, like hypothetically, another beam-like body like this, and it will be connected via a revolute joint, then you would look at what's going to be the angle difference between these two bodies. And this is something that is called relative coordinates, typically used in robotics. We are not going to discuss about this kind of method that are based on system topology, but we are more making a use of this kind of the more straightforward global coordinates. But again, there are these other methods, and there you can go back and forth between the different methods. So if not happy with this selection of variables, you can make a use of these relative coordinates. And they are generalized kind of like mapping that you can convert one to the other for your information level. I don't know if you guys care about this information, but now you know. At least you've been told. Let's put it this way. Okay, so two components that comes along. Again, mass multiplied by acceleration and quadratic velocity vector. That's it. Now, if you take a close look about these components, the mass matrix consists of three different components. First of all, the mass matrix, let's say the submatrix that is located in a mass matrix, located here in the upper left corner, is going to be diagonal matrix, which is the diagonal component are such that they are the mass of the body like this. So this is 2 by 2 diagonal matrix. So off diagonal components in the submatrix are zeros. Diagonal components are representing the mass of the body. Makes sense because columns and rows associated to this particular components are translation in x and y direction. Inertia have to be related to how heavy is the mass. So if you want to have a translational acceleration, what matters is the mass of the body, nothing else. Then the one that is located here in the lower right corner is a mass moment of inertia. Mass moment of inertia is like how much the inertia is resisting the rotation. That depends where you are rotating with respect to. So if you're rotating with respect to coordinate system that is in the middle of the bar, resistance is less than you have a coordinate system that is located end of the bar. Now keep this in mind. Like regardless where you're going to measure your inertia component, or let's say the mass matrix component, the mass, this one will be always the same. So it's not possible that human being will weight differently depending how you measure it. Like if you measure my body weight using my right leg or left leg, is the same body weight. Doesn't change. Whereas the inertia will change because then we're looking where the rotation is with respect to. Okay? Now, the third component, it's the one that is located here, is a vector, and it is a transform form of the vector is located lower here. This is the one that combines translation and rotation. This component, this off-diagonal component, this one, let me change the color because that's going to be my first in-class quiz. This component becomes to be equal to 0 if the body reference coordinate system is located in the center of the mass. Now, if I have beam-like body like this, center of the mass is located in the center here. So if I place my body coordinate system to the same location, regardless of the orientation, this component, which is this off-diagonal component, becomes to be equal to 0. That's what's going to happen. Same will happen to quadratic velocity vector. That too will disappear. Not disappear, but it's going to be equal to 0. So it kind of you can neglect. Okay, so this is a mass moment of inertia, and how is my recommendation to you to compute the mass moment of inertia is please make a use of pre-calculated tables, because there's plenty of them. You say that those are given to you already in high school, I guess. In high school there's a lot of, if not earlier, there's a lot of these tables that they kept telling like how much is the mass moment of inertia in different bodies with respect to different coordinate systems. So make a use of that. And if you don't see your body coordinate system to be located exactly how in those pre-calculated tables, use a parallel axis theorem. Parallel axis theorem, something that is explained in the lecture note. So take a look at that. By the way, another day I look at the lecture notes, and I don't know if you guys printed out or not, but I recommend, because I was surprised, like it's a good stuff. It's a good stuff. Take a look at it. It's going to be something that of course there's a high risk involved, because once you get started, you might not be able to stop yourself. You might not. So you're careful with that. So you're leaving your, you don't eat anymore, you don't sleep anymore, but you're just reading the lecture notes. Can happen. Can happen easily. So go easy with the lecture notes, but still highly recommended to print it out. Keep it with you, because there's another way of things explained there, and I think that you can make a use of that. Okay, so that's the mass matrix. Quadratic velocity vector, it is a force vector that is imposed to the coordinates the x coordinate and y coordinates in the global coordinate system, so Rx and Ry. So it's like how much the body reference coordinate system experiencing the centrifugal forces because of the rotation. That's what it is. So now if you have your body reference coordinate system located at one end of the beam-like body, and you're rotating your system using this angle theta here, how much you experience that the force is like this. That's what it is. When the body reference coordinate system is located in the center of the mass, you experience nothing. You do not experience centrifugal forces because you're standing in the center of the mass. And when that's the case, then this quadratic velocity vector becomes to be equal to 0. It's a 0 vector in that particular case. Okay, when you're going to get the diagonal mass matrix? You can get the diagonal mass matrix when the body reference coordinate system is located in the center of the mass. Center of the mass. Center of the mass. Okay? You know what's coming next. Okay, so it needs to be located in the center of the mass, and your quadratic velocity vector becomes to be 0 for the same scenario, when the body reference coordinate system is located in the center of the mass. Center of the mass. Center, now I cannot repeat it anymore, because now we're in a first in-class quiz. The first in-class quiz is on. So mass matrix of a body is a diagonal matrix if body reference coordinate system is located in the center of the mass. Body reference coordinate system is located outside of the center of the mass, but within the boundaries of the body. Body has a beam-like shape. Body reference coordinate system is located outside of the body. So these are the 4 scenarios. One only is correct. Okay, I think the in-class quiz is on. Is it? Okay, so should we take a look at this one, or should we take a look at the next in-class quiz? Because the next one is something that is kind of related. Quadratic velocity vector is a 0 if, and again, the same scenarios. So the body, no, but the different order this time. Body has a beam-like shape. Body reference coordinate system is located in the center of the mass. Body reference coordinate system is located outside of the center of the mass, but within the boundaries of the body. body reference coordinate system is located outside of the body. So these are the 4 options, same options than in the previous in-class quiz, but in a different order. So let me put myself back here. So this is what I asked in the beginning. Now, I accept nothing but the 100% success rate. Okay, are we guys? Okay, let me see if there's any. All right. What's up with this one? There. I need to make this a little bigger. Here's my circuit tape. Okay, good number, very good number. So this smells like a big success. It smells like something that there's going to be, first of all, look at the number of students. So it's going to be, there's a lot. There's a lot. You know, we've been scoring the highest, that was 90. Rest, we don't care because they don't want to play with us. We don't care. And look at it. So it's one more student missing out of there. So it's one student shy from 90. And that's a lot. And then not just that, but success rate 100%. I saw this rector in the corridor, so I'm going to run after the lecture and come here. He needs to hug each one of you if we're going to score 100%.
It will be almost.
You don't think it is 100%? 91 students, and this is how the 100% look like. What? So, okay, but you need to round it up things. You need to round it up. Because this, you round it up, it's going to be 100%. Good news is this. I don't need to go to see the rector because he already saw me. When he saw me, he was looking very bad eye. So he was like, okay, what's up with Aki? So, okay, good. That's good news. Still very high. But what about this? Now, guys, please, make it happen. Make it happen. Okay, so you guys are going to think this over, and I'm going to continue. You see the options here. The options are in a different order than in the last case, in a different order than in the last case. Note that they are in a different order. Okay, so we go for this guy. So we continue with the story. We continue with the story. We were there, and now what's going to happen is equations of motion. So that's it. So we have all the components needed, because what is that we are after? So we, like I mentioned a week ago, so this is how the equation of motion eventually going to look like. So there's, let me think, there's a transpose here. Okay, it continues. Sorry that my handwriting is not very clear today. Okay, so this is an equation of motion. What are the components we are already familiar with? So we know this guy, this is our middle name, Jacobian matrix. So he's a good friend of us. So we know that back and forth. Jacobian matrix with a transpose. This is a zero matrix, there's not much to get to know. So again, we know this one, we know this one, we know this one. Mass matrix we learned a week ago, so that's a clear thing. So we know this guy, which is a generalized coordinates. We do know this one, which is a generalized external applied forces. We know this guy, which is a quadratic velocity vector. So the two unknown components are Lagrange multipliers, which is this one, and something that is called QC vector. Those will come in a play next. So I'm going to introduce you first Lagrange multiplier, and then eventually, once we're done, I'm going to introduce you to QC. Okay, Lagrange multipliers, for your information this time, it's going to be related to constraints. So we need to find a way to incorporate the constraints. So the situation is kind of like this. So we have equation of motion that can be written like this. And then this is equal, okay, let's just put this equal to 0, which is not exactly the case right now. And then we have constraints. This is our set of coordinates, which consists of differentials and algebraic equations. So how we're going to come up with this kind of set, and then we convert this to be ordinary differential equations. Okay? But first, what we're gonna do. So we're gonna take all the bodies in our system into account, because in a multi-body system, as the title implies, consists of multiple bodies. Okay? So what we need to do for each of these bodies is that we need to take the virtual work done by each of the bodies into account. So this is a concept that is different that, for example, in a finite element procedure, because we're going to keep on adding the coordinates. We're kind of going to be adding the work done by each of the bodies simply by keep on adding the number of unknowns, which is conceptually different, like I say, like in many other computational procedures. So this is what you're going to get. You're going to have here generalized inertia forces minus generalized external applied forces. That's the kind of like this way. Remember what we discussed in the very beginning. The same story, but the difference is this. This is expressed using global coordinates. This is the same, but using generalized coordinates. And what we really after here is, of course, this one. We still have a problem here, because the problem is that in this equation, we are not taking constraints, these motion limitations into account. So that needs to be accounted one way or another. And of course, we have multiple ways to take that into account. But anyways, so let me first explain you how you can construct the system mass matrix and system quadratic velocity vector and system vector of external applied forces. Like I said, you do that by keep on adding the coordinates. So this system mass matrix is called like a block diagonal mass matrix, but it's not sharing degrees of freedom. And why is this? Simply because if we have a vector of generalized coordinates, it consists of unknowns related to first body. This is one. Unknowns related to second body, and so on and so forth. So we keep on adding the length of the unknowns based on the number of bodies in a system. Okay, guys, how many bodies, how many coordinates each of the bodies needs? 3. Okay, so team 400 euros car, so you guys need to look at me too. So you need 3 bodies. It's going to be 3 generalized coordinates per each body, okay? If you have 2 bodies, how many coordinates you need? 6, so on and so forth. The same holds here. So now if you have, let's say, a total of 3 bodies, what's going to be your size of your mass matrix? 3 by 3. It's going to be 9 by 9. Because we keep on adding, this is going to be, this submatrix is going to be 3 by 3. This submatrix is going to be 3 by 3. This is going to be 3 by 3. And if we have a total of 3 bodies, then their final dimension is going to be 9 by 9. Okay? The same, if we're going to have here 3 bodies, what's going to be the length of quadratic velocity vector? 9 units. And if it is external applied forces, it's going to be 9 units. Okay. And then we have the vector of constraints, which is kind of separated. So we have equation of motion, and then we have a constraints. And something needs to be done. We are not happy the way things are because they are not accounted yet. So they are like separately accounted, but we need to put them in the same package where the equation of motion and constraints are simultaneously accounted. Simultaneously accounted. All right? And that's what we're going to look. Now, here's the whole story when you're using this very sophisticated way of virtual work. So you have virtual work of the entire system, inertial forces, external applied forces. This is eventually how things will be written. Now, here comes something that you have not heard before, because the concept of virtual work is very often misused, and it's misused exactly in the way that it is explained here. So you're saying that this equation is going to be equal to 0 regardless of what? Regardless of the scenario. And this equation can be set to be equal to 0 in a certain scenario only. In a certain scenario where the virtual displacement, this one here, have to be kinematically admissible. Kinematically admissible virtual displacement will be something that if you have, let's say, the box that is connected to ground via translational joint. kinematically admissible displacement would be moving this back and forth in a way that I'm not violating against the constraint. But that's not the same than this one, because this one is saying virtual displacement of all the generalized coordinates. If I do it as it is mentioned here, I would also introduce the virtual displacement like this. That's not kinematically possible because the constraints are not allowing me to do so. Or I can introduce the rotation of the box like this. Same story. That's not kinematically admissible. So this equation, so if I continue the story, this equation, generally speaking, is not equal to 0. Why not? Because the virtual displacement is introduced to all the generalized coordinates, and we are not accounting the constraints. So this is a big problem. So we have to express this in a way that it is kinematically possible, which is a little involving. So this is a task we can make it happen. But we are not going to do this today. So we can use something a little different than that. And that's kind of what we're aiming here. Again, so let me try to summarize this because you guys need to listen to me right now. So this is what came out from the concept of virtual work. And generally speaking, we cannot set this to be equal to 0 because this one here, we introduced in the virtual displacement to all the possible motion scenarios, which is typically not possible. Again, so if I have here crankshaft mechanism, and I'm going to take a look at this, let's say that I'm going to take a look at the connection rod like here. The connection rod can move in a certain way because of the constraints. And I cannot just say that you go and move any way you want, regardless of the constraints, because I would violate against the constraints. Now, this is what I'm going to take a look at the next. So I'm going to express this in a way that I'm going to take constraints into account. And again, mathematically, we have two possibilities. We can either substitute the constraints inside of the original equation, or we can add the constraint to original equation with help of, correct, Lagrange multipliers. So those are the conceptual options that we can deal with. Today we're going to deal with the one that we're adding the constraints to original function with help of the Lagrange multipliers. Alternatively, we could substitute the constraint inside of the equation, but that's going to be mathematically a little bit harder than the one we're currently going to take a look at. Okay, now let's take a seat and see how we are doing in terms of in-class quiz. So this is it. Quadratic velocity vector is 0 if what? What is the correct answer? So it's going to be B is the correct answer.
Better from the last one.
Yeah, we are moving in the right direction. That is correct. But what is with this 1%? What is this? What is up with the 1%? So somebody wants to be a different kind of the individual, I believe. Okay, that's incorrect. Good news is this. No one is voting the option B as a being-like shape. That doesn't matter. Shape doesn't matter. Okay, so let me take myself back here. My next question is this. Equation that we just looked cannot be set equal to 0 because something is missing, something we have not accounted. Now take a look at this equation, and see, take a look if we are taking inertial forces into account. Are we taking inertial forces into account in this equation? Are we going to take the external applied forces into account? Are those accounted? And are we going to take constraints into account? And are we going to take no forces into account? No forces are accounted. So these are the four options. Okay, the question is not on. So let me put it on. This one. Okay. And then what follows is that we're going to make a break of mechanics. Good news. So we are not going to look at the mechanics for the next slides, but instead we're going to take a look at the subject matter that we like the most, mathematics. How you guys say about that? Yeah, I can tell for online participants that people are smiling a lot. They're very happy here in a lecture room. Some of them are crying because of the happiness. So that finally they can leave the mechanics behind and focus on mathematics only. Okay, but this one, what is correct? What's the correct answer? D. C.
Yes. Constant.
Constraints. Seriously, guys? Okay, all right. So we got last time it was it like 91 answers? So we can wait another minute, and then we're gonna go. And then let me just to show you what follows is mathematics. So I want you to revisit your mathematical notes. You remember when you were in elementary school, they mentioned that, okay, there's this optimization problem that you need to minimize the function such the way that the constraints is accounted. This is exactly what we're doing here. Same story. And if you take a look at your notes from elementary school, you soon remember that there were two options. You can substitute the constraint, which is this one, inside of the original function, and then you can differentiate the original function, and this is the one way to find the minimum. Or you can add these constraints to original function, which is this one, with help of Lagrange multipliers. All remember this story. Or was it so many years back that you don't remember this so well anymore? So many years back that you don't remember this so well anymore. Okay? Okay, so we're going to take a look at that momentarily, but before that, so we got all the answers in. I don't think it is 100%. 80. I'm thinking it's as low as 70. Okay, so it's 80. Okay, just switch down to 84. It was 85. Somebody was just entering the incorrect answer. But constraints are not accounted. So we have to take constraints into account. The problem is that we introduce in the virtual displacement all the coordinates, not considering constraints at all. So the choices are pretty much what I'm going to explain in the case of mathematics. So we can introduce the constraints, our original equation, which is exactly this substitution technique. So we can take this constraint, substitute it here, or we can add it, the constraint, to original equation with help of Lagrange multipliers. Let's take a look. Okay, the first option, very simple. You know, this is my original function here. Gonna change the color. This was my original function. This was my constraint equation, if you may. And the constraint equation was something like y1 minus y2 must be equal to 1. This is mathematics. No relation to mechanics, what we have discussed earlier. Okay, so once I'm solving the y2 from this equation and substitute it back here, this is how it's going to read. So this is y1 power 2, this is y1 minus 1 power 2, then that's going to be then equal to 0. How is that I can get the minimum of this one coordinate, which is a y1 in this case? I simply differentiate this with respect to my variable, which in this case is a y1. Okay? Again, I don't recommend you to differentiate this. This is not the hardest differentiation, but still, you guys make a use of symbolic math tools because they will do it automatically for you and they will do it correctly for you. Your pen and paper can do it slowly, but typically incorrectly. Okay? So you differentiate that, you're going to get the y2 multiplied by y1 minus 2 equal to 0. Now, this is where you can get, this is where the extreme point is located at. Once you're solving this, you're going to get y1 is equal 1 divided by 2. Then you're going to redo the whole story, but this time you're solving the second component, which is a y1. Here, you take this in another side of the equation and you substitute the result to here. This is how it reads. And then you differentiate it. Now, the only variable that you deal with is going to be y2. And then you have to differentiate that with respect to y2. This is what you're going to get. So it's 1 plus 2 multiplied by y2 equal to 0. Extreme, again, can be found when you put this equal to 0, like it is shown here, and you're solving the y2, which is a minus 1 divided by 2. Nothing new here. This is what you learned already in your childhood. So nothing special here. But you might have forget that there's this alternative. An alternative is this, that you don't substitute the constraint within the side of your original function, but you make use of the Lagrange multipliers. Okay, this is a graphical representation of the story, which may be a little hard to understand. But what we are after here is that we have a trail here. This is like a hiking. In a hiking that goes in a map. So hiking this trail here is shown in this orange, almost like a red color. You have to stay within this track. And why is that? Because this is your constraint equation. You are not allowed to go away from your constraint equation. And now the challenge is that you need to find the location, which is this track is in the highest possible altitude. And these are the contour course or descriptions. This is where you're getting higher and higher. This is obviously a hill. You're taking your trail all the way up to the summit. You need to find the position which is the highest possible altitude in your trail. Again, you cannot step off from your trail. You cannot step off from your trail because you have to respect your constraint, like this. Okay, you're getting started here. You're gonna go like here. You see that the hill is continuing uphill. So it continues uphill, it continues uphill. You make a use of you kind of taking a look at how is the contour of this map, and you're looking the contour of this trail. When these two vectors are in the same location, this is where your summit is located at. This is the highest altitude within the trail. That's where it is located at. So what are these slopes? This one here is something that you're differentiating your constraints, and this is something that you're differentiating your original function.
You are not able to see.
So what is that you'd missed?
When you remove the lines from.
How far was this? Okay, let me see if, you see this? No. What is this? Huh. Okay, just a second, let me, nothing. It's not, what about online participants? Can they see this? No, they cannot. Okay, hold on. Let me check this. Just a second. Good point, because it makes it a little hard to follow my explanations. Okay? Yep. Okay, so we're back in the business. Okay, so guys, what did you miss?
When you remove the line.
Okay, when I was starting to removing the lines, then it disappeared.
Yes.
Okay, but that you remember the story that you are in this trail, and you're forced to stay in this trail. You are not allowed to move away from the trail, because the actual maximum of the point will be here. But that's not cool, because you cannot go there, because, like mentioned, you have to stay in this trail. And what is this trail? That's a constraint. That is your constraint. So what you need to keep on doing that you need to compute the slope of the trail and the slope of the hill. And when these two slopes becomes to be parallel, maybe pointing the incorrect directions, in opposite direction, but when they become to be parallel, this is where the highest point within the trail is located at. So again, you keep on computing these differentiation, these slopes, and when these slopes is matching with the slope of the hill, that's where you are located at. Now the only problem we're facing here is that these slopes are having the opposite direction. To make them completely parallel, and also they might have a different length. So to make them completely parallel, one of these slopes have to be multiplied by unknown variable. which is going to be called Lagrange multiplier. Okay, one more time, and then I'm going to leave from this story. So you're in a hike. You have a map. You're reading your map, and you have to stay within your trail. You keep on going uphill all the time, and you keep in checking like the differentiation of your constraint equation. Like, is it coming upwards or downwards? And as soon as you have this like a vector that is pointing the same direction, or let's say the opposite direction that the hill itself, that's where the highest point is located at. You just need to match these two vectors by multiplying one of them by something that is called Lagrange multiplier. Okay, now if you heard this, you're hiking on the trail, that's okay. That's okay, because that doesn't matter. This was just if you do the hiking. If you're not hiking, if you're more like city person, fine. That's fine. Because for city person, we're going to take a look at the math. The math is this. So this is a delta of the original function. This is a delta of constraint equations. And then this is the one that is making them to be equal in the length. This is where the minimum is located at. And then we have to take one more thing into account. And one more thing into account is that we have to take this constraint because we have to stay within the trail. This is what we need to minimize next. This is where these two gradients are parallel. This is where you stay within the trail, mathematically expressed. Okay, how the same problem what we looked at a little while ago. This is my original function. This is my constraint equation. How can I make a use of the same story, but in case of this mathematical scenario here? Okay, mathematical scenario, we have to compute a delta of the original function, which I'm simply taking my original function here, differentiating that with respect to my variables. And what are the variables this time? This t vector consists of two components, that is y1 and y2. Okay? Of course, this is a scalar. This is again scalar. This is a vector. So when you do this differentiation, you're going to get the vector, not the matrix, because this is scalar instead of vector. You're going to get these two components. Simply differentiate this with respect to y1. You're going to get y1. Differentiate this with respect to y2. You're going to get y2. All right? Then I'm going to take my constraint equation, and I'm going to do the same. I'm going to compute this gradient of the constraint equations with respect to my variables. You're going to get 1 and minus 1. Okay? You're still with me? So now comes the way we're combining them together. So we're going to combine them together by making a use of this equation that you look a little... Okay. Sorry, let me write a little bit differently. This was a q, was a lambda multiplied by t. So when you do this, this is how it reads. This is exactly this notation here. And then you just take a constraint into account. That's the final piece of information we need. And why we need this final piece of information? Because what happened is that I keep on increasing the number of unknowns. It was originally y1 and y2, but now it's no longer that, but it's added by one more component, which is lambda. So lambda, that is corresponding my constraint equations. And now, here is my set of equations. I have three unknowns, three equations. It's a matching number, so I can solve the whole system. So now if I take a first equation, solve lambda from that, then I'm going to get the second equation. That's going to be lambda 2. So then it means that lambda minus 1 minus lambda minus 1, lambda is going to be 1. So it's going to give me the lambda is going to be minus 1 divided by 2. And it's going to give me exactly the same location than in the previous case. Now what we learned. So we were able to get the same extreme location, same location of the summit, but we got one extra value, which is this lambda, these Lagrange multipliers. which mathematically is the price we have to pay because of the constraint. If I take myself back, okay, this is going to be a little bit confusing explanation, but remember the actual summit would be located here. But we are not able to go here, but this is we're going to find it here. This one here is a price we have to pay because of the constraints. What is that in the mechanics? Well, if you have the pendulum like this, because of the revolute shown here, this price we have to pay because of the constraints are reaction forces due to the constraints. Reaction forces due to the constraints. Okay. Very lengthy story, very painful story. And now you guys are thinking, okay, it's going to be, when we're going to make a use of this thing, it's going to be very difficult. That's opposite. It's an opposite. It makes things easier because adding constraint is something like, let me tell a story. Like the multi-body community, there has always been two strong communities. The one that is American community and one that is a European community. And they have a disagreement what is the best way to go. There's no such thing like what's the best way to go, but the American community is always according to these Lagrange multipliers because it keeps things simple, but it's just adding the number of unknowns. But things are very simple, whereas the European community is always favored for substitution. Are we American or European? Asian. We are Asian. That's a correct answer. So we are taking the neutral ground here. So we are, in this particular case, we are supporting the Asian community. Good answer. Okay, but honestly, I'm leaning towards Americans. Why is that? Because my education is from US. That's why. But I'm living in Europe, so should I leave my background and focus on the Europeans' way of thinking? I'm not sure. But it makes no difference because either way, response is always same. So never ever responses are based on the equation of motion you decided to use. Okay, so my proposal is this. So we're gonna make a use of this what we just learned in a case of multi-body system dynamics. So this was a whole concept of Lagrange multipliers. So that's what we're gonna do. And when you take a look at these components, what are these components? They're actually something that we are already familiar with. So we have here, this is original function, which is inertia forces minus external applied forces. We knew this already. And what is this? This one here, when you differentiate your constraints with respect to your variables, something that we are already familiar with. This is Jacobian matrix. Because Jacobian matrix, remember, was this. This is the constraint equation. This is unknowns. When you add them together, now this is how it reads, and that's it. Now we kind of have an equation of motion because we have here constraints taken into account with help of Lagrange multipliers. So we add in the constraints original equation, and that's how we're gonna find the extreme location. Okay, now you guys, if you still find your way away from the lecture room, how many minutes you need? How many hours you need to recover from this? 1 hour. 1 hour. Yeah, today I don't know if you noticed that I mentioned that we have this question and answer session getting started at 6 o'clock. But today I need to leave early from my office, so I need to leave at 6:45. So it's only going to be 45 minutes today. Because I have family businesses to take care of. So I need to start pedaling back home already 6:45. Okay, but now break. Think about this during the break, and then we're gonna get back to this, and then we're gonna run the whole story. We're gonna make use of the equation of motion. Okay?
It means that we are to finish off this week. Too much to study. Two classes.
So what did we mention? Like how much time we're gonna have? How long is the break?
I don't know.
So did I not mention that?
You didn't see that.
Really?
Yeah.
Yeah. My memory is so bad that I shouldn't work anymore. So
We are on one on track.
one long break or one short, I don't know. But we just wait Team Finland to come back and then we're gonna go again. How come it's not showing the same that I see here? Yeah. Okay, so this is again not, this is where I should go easy because every time that I have a break, easily makes things less clear in my online presentation. Okay, so let me take a look. Yeah, it's perfect. Okay, we were here, so we left here. Okay, so we almost done with the story. We still have one problem, and one problem is this. Now the way the equations of motion is expressed, so we have too many unknowns. Why is that? Because we have equal number of equations that we have number of generalized coordinates. So that's okay if that only would be a number of unknowns, but that's not the case here because this one here, which is a reaction force due to the constraints, is an unknown as well. So this is not enough. So we need to make a use of what we just discussed earlier. So we need to make a use of the constraint equations. Now we have a matching number of equations and unknowns. So here we have unknowns, which is there's a acceleration of generalized coordinates and Lagrange multipliers. And once we take constraints into account, then it match. Why they match? Because the number of Lagrange multipliers is always going to be the same as the number of constraint equations. Number of reaction forces will be always the same as number of constraint equations. This is it. So this is going to be something that is called set of differential algebraic equations. Problem is that if you look at the time integration schemes that are available out there, most of them are not made for this kind of the system. There are some that are good for differential algebraic equations or system of differential algebraic equations, but most of the time integration schemes are used to deal with the ordinary differential equations. And this is not that form. So what we can do then is that we can convert this equation to be in a form of ordinary differential equations. That's going to be happening in a way that we're going to make a use of the constraint equations. We're going to differentiate them twice with respect to time. We're going to be able to introduce a new vector, which is called QC. No physical interpretation, no clear physical meaning, but this is something that helps us to convert differential algebraic equations to be ordinary differential equations. Now, if I'm going to introduce this very last component, I'm able to convert this one to be expressed like this. And this is the equation of motion. Remember, this is a mass matrix. This is a Jacobian matrix. Jacobian matrix transposed. This is a zero matrix. This is acceleration of generalized coordinates. This is a Lagrange multipliers, external applied forces, quadratic velocity vector, and the QC to make this conversion. What is going to be the vector of unknowns? It is this one. The vector of unknowns is no longer just the generalized coordinates, but generalized coordinates plus constraint equations expressed by Lagrange multipliers. Okay, so now if I would have a system like this, sorry, that is a little bit unclear drawing, but it's a pendulum, one moving body. How many generalized coordinates? 3, because every body needs 3. How many constraints? 2. So it's going to be 3, 2. What's going to be the number of unknowns? 5. Because this is unknown, like expressed here, and this is unknown, like expressed here. Not the constraint. Okay, let me correct myself. Constraint is not unknown, but how much is going to introduce the reaction forces, that is unknown. That is unknown. And that is expressed by Lagrange multipliers. This is this guy. So the number of unknowns is total of 5. 5. Good. Now, this is a whole story in short. This is where we're introducing the Lagrange multipliers. We're going to take the constraints into account. Once we differentiate in constraint twice with respect to time, we're able to do the conversion from differential algebraic equations to be ordinary differential equations. That's the end of the story. That's it. So we reached the final conclusion of the class. Only thing left is we need to train this couple times, and that's it. Then you're fully educated what comes in computational dynamics. Not fully educated, but let's say that you know at least one method, you know all the components, you know the concept behind. Let me tell you this. What's the course that is the most hated course in history of the universities? Dynamics. People hate it big time because it's so complicated, so no one figure out how the dynamics works. So once we're done with this story, you guys are not just the expert of dynamics, but computational dynamics also. So it's okay to walk like a couple days like Michael Jackson did, like moonwalking style, like celebrating this big accomplishment, because it's a big deal. and then you need to start working like others. But this is a big deal. Big deal. Okay. In augmented formulation, unknowns are acceleration of generalized coordinates, and augmented formulation is the one that based on Lagrange multipliers. Acceleration of generalized coordinates, Lagrange multipliers, generalized forces, acceleration of generalized coordinates, and Lagrange multipliers. Which one is the correct answer? These are the 4 choices. And let me take myself to the in-class quiz. And then we're going to take a couple more in-class quizzes, and then we're going to simply practice what we just learned. Here. Okay, in augmented formulation, that's a method based on Lagrange multipliers. What are the unknowns? Pretty easy, I would say. Okay, so would you like to see this more, or can I go? Because what I would like to do next is this. I would like to practice what we just learned. And I'm going to solve, first what I'm going to solve is that I'm going to solve the dynamic response of this complicated mechanism. So it's almost like a pendulum, but it's more complicated than that. So it's a system that consists of one moving body that is constrained in a primitive joint here. So this can go up and down. And this can go left and right. So this is going to be my mechanism. So this is applied by gravity. So the gravity force only. So nothing but the gravity. So how this works. So what we're going to do is that we're going to follow the certain steps. And more or less automatically, once we completed those steps, we have an equation of motion. Now, here comes something extremely important to understand. No thinking. Following the steps. No thinking. Just following the steps, and it's going to be fine. It's going to be automatically correct. And as soon as you start thinking those shortcuts and clever ways to go, you're going to make a mistake. So what we learn, no thinking. Very systematically go with one step to another, and then you end up to have an equation of motion. Okay, first step. First step is, in this example, the number of unknowns is what? Okay, let me first take this off. I'm going to take a look at the in-class quiz. Okay, we got 83 students here, so can I think that I will close this one. There are last ones coming in. Because I'm kind of in a hurry, because I still have my examples to show. Okay, so now it's 87, 80. Okay, last ones, guys, please speed up. Success rate, 95. 95. 90, 99. 99. Okay, 99. 93. Okay, I understand this is confusing because it is true that Lagrange multipliers are unknowns and acceleration of generalized coordinates are unknowns, but I say one all is correct. Did I say that? I don't think that I ever mentioned that. Okay, meaning that the success rate is 100%. Hey, so look at that. So we made it. So it's 100% success rate. Because I hope, I'm not going to take a look at the recordings afterwards, but I hope that I did not mention that one option only is correct. Good news. We made it. Kind of. Okay, what about this? Okay, this is where I have my high hopes. And I'm asking this. In this example, the number of unknowns is 1 as a one moving body, 2 as a two-dimensional system, 5 as a 5, 99 as because the bigger the better. One only is correct. Now, one only absolutely is correct. So only select one. But which one? The option that there is a 3 generalized coordinates per body is missing. As a 1 degrees of freedom system, 2 as a planar system, 5 as a 5, 99 as a 95, 99. Okay, so what's going to be the success rate of this? This is 100. That's absolutely right. So this is a 100% success rate. But you guys are still thinking. So while thinking, let me show how to solve the response. Okay, steps. These are the steps. Number 1, mass matrix. Highly recommended that do not think too much. Just take a pre-calculate tables and that's it. First, I need to take a look at the 2 by 2 matrix that is located in the upper left corner. So it's going to be diagonal matrix where the mass of the body is located in the diagonal components. Then I need to compute the mass moment of inertia. I don't recommend you to compute it in this hard way, but just take a pre-calculate tables and that's it. When you do so, you're going to get the mass multiplied by length power 2 divided by 12. Because this is the lowest mass moment of inertia you can get for the body like that, because the body reference coordinate system is located in the center of the mass. Okay? Then this, the one that is off diagonal component is going to be 0 because the body reference coordinate system is located in the center of the mass. This is my mass matrix. Constructs into Jacobian. What are the components in Jacobian? I need to get the constraints, and I need to differentiate my constraints with respect to my generalized coordinates, which are here. Okay, constraints are located here and here. So what should I do for that? I said just simply should go each of these locations with help of the equation, the only one that I know, this one. So first I'm going to go here, and then I'm going to orient myself according to the body reference coordinate system, and then I'm going to make my last leg with help of vector u bar. Okay, so let's take a look at the point P, the one that is here. So I'm going to first travel the origin of the body reference coordinate system, taking orientation into account, and the last thing is a vector u bar. Look at how the body reference coordinate system is pointed. This is x that is pointing downwards. This is y that is pointing transverse direction. So how much I have to travel to reach this location is going to be x minus L divided by 2, y 0. When I substitute that information here, when I'm setting this, the motion in a global x direction is constrained. This is not possible, meaning that this one here have to be 0. So when I do this math, it's going to give me this constraint equation. Make sense? Second one, located, maybe I need to take some of the drawings away. Okay, so the next point is this one. Same story. So I'm going to first travel the origin of the body reference coordinate system. Then I take the body orientation into account. And then I'm going to make my last leg with help of the vector u bar. Vector u bar obviously is L divided by 2 because x is pointing downwards, and then the y transverse direction 0. That's going to keep, and again, now the motion in the y direction is going to be 0, so that's going to give me my second constraint equation. That needs to be differentiated with respect to my variables, and here's my Jacobian. Done. Step number 3. Generalized external applied forces. I say only one force applying the system, gravity force, pointing downwards. So that's the only force in the system. So what I need to do is that I need to identify where the force is applying. It's here. Vector u bar here is 0. When I differentiate that location with respect to my variables, it's going to give me the magic mapping matrix, which is not very magical this time. It's identity matrix, and then the 0 matrix, 0 vector. Let me correct myself. And then that's multiplied by gravity force, which is having the component in a y direction only. And it's going to be mass multiplied by gravity constant minus in a sign, because it's pointing downwards. This is my generalized external applied forces. Quadratic velocity vector is 0. I don't need to care about that. The one thing left is this vector QC, where I have to differentiate my constraints this complicated way we learn when we compute the kinematics. So here's the Jacobian multiplied by velocity. That is then going to give me the vector that is differentiated with respect to my generalized coordinates. This is what I'm going to get as a result, this one. And then that is finally multiplied with velocities. It's going to give me the vector of two components. Last thing to do is sampling. So this is my already inverted, like semi-inverted. This is my mass matrix. Jacobian with the transpose. This is my external applied forces, and this is my QC vector. I'm good to go. I can solve here my position. I mean, first the velocity and then position, and that's it. Would you like to see it? Okay. Ready. It comes here. Oh, this is so small font that I don't see this so well because I'm so experienced that my small fonts are not willing to collaborate with me anymore. So what this says, okay, I think that it's, okay, good. So it was able to solve it. So let's see if we can visualize. This is a visualization. Let me make this small enough so it's not blocking the view. We're like here. Okay, ready? This was incorrect, so I don't want to use this one. So let me see. Okay. Not good, because this is not what we wanted to solve. I'm experiencing technical difficulties. Actually, I'm not experiencing technical difficulties, but I did not make a preparation good enough because this is now the pendulum. I don't want to solve that, but I want to solve the system that is slightly different than we just looked at. We can correct the file, or we can just take a look at another example, and I can solve the correct response next week. Which one you want to go? Next week, because you are rushing yourself back home, I guess. Okay, good thing. So you're going to see the MATLAB solver week from now. And this is going to be something that is going to be so straightforward that any mechanism in your life from this on, you can solve it, if it is a planar case. Three-dimensional case is a little bit more complicated than that, but just a little bit more complicated. Okay, that's it. My next mechanism is this. So it consists of two moving bodies, one revolute joint here, another revolute joint here, and one primitive joint here. How many generalized coordinates? 6. How many constraints? How many constraints? 6. Guys happy? 5. You're saying 5? Okay, 5 is an alternative. Any other options? 3. Okay, so it's a little bit unclear writing. Okay, Team Asia is changing that from 6 to 5. Okay, you sure about that? Team Finland is saying 5. Correct answer is 5. How many unknowns?
11.
Okay. All right. So okay. So let me take myself here. Okay. What was the success rate here? I think it was pretty high. So because correct answer was 5. Okay. 1 has a 1 degree of freedom, or wasn't what I was asking. 2 was a planar case. Makes no sense. 99 got 1 vote. I think we have somebody that is locking in the system and intentionally answering everything incorrectly. But keep this in your mind. You can play as much as you want, but it is affecting your final grading. So I don't know if you're going to laugh so much if you know that, because not so much fun. Okay, this one. Okay, you want to see the mechanism again?
No, it's okay.
This is how it look. Now I have two forces. I have 1 point force applying here, and the gravity that is applying to both of the bodies. Okay, so the number of unknowns in this case is how much? Okay, let me take a look at this one. Oh, you guys are not yet ready? Okay, so while you guys are thinking, let me show how you can create the equation of motion. What's the difference between this example and the previous example? No difference. No difference. You're going to follow the same steps over and over again. What you're going to get automatically is going to be your equation of motion. Again, we're going to get started from the mass matrix. That's going to be the number 1. Jacobian matrix, number 2, so on and so forth. So no exceptions. Always the same procedure over and over again. Okay, first mass matrix. This time I'm cutting the corners a little bit. So I'm just telling you how is a mass matrix because look, this one, beam-like body, and the body reference coordinate system is located in the center of the mass. Same here, beam-like body, it's here. So it's going to be diagonal matrices that I'm going to get. Diagonal matrices for this one and this one. And now I went too far off. Here, this is how they look. And I just need to assemble them as a block diagonal assembly. So it's going to be, here's the first body. Here's the second body. They do not overlap. Those of you that are in a finite element formulation, you know that in a finite element, if you have like two neighboring elements, they do share same degrees of freedom here. And this is where the stiffness matrices are overlapping. So the system stiffness matrix would be something like one stiffness matrix here, another one here. And they're overlapping here, which is corresponding this particular location. We don't do that. We don't do the overlapping in multi-body system dynamics. So we say that they are completely separated. A possible, yeah, go ahead.
Why over 12?
What is that?
Why is it over 12?
Why there is a,
Because of the shape.
Shape?
It's the center of inertia. The
so the question was again, what was the question again?
At the corner, why is it over 12?
Why is it divided by 12?
Why this is divided by 12? Okay, because this is a mass moment of inertia. Remember that when we compute the mass moment of inertia for beam-like body, this was something that this was a mass length divided by 12. I understand something that I haven't kept my promise. I said that if you guys, somebody's raising a hand and say something is unclear, that's going to be worth of, what did I promise? Was it like lunch? Coffee. Coffee. I owe you coffee. You drink coffee or tea?
Coffee.
Coffee. Okay, coffee with or without me? So is that like coffee with or without milk? Coffee with or without aki? So I don't know, how are you consuming your coffee? With milk, but with or without aki? So you can don't answer right now. You can think about this later, and we get back to this next week. Okay. Others, same option, and it can be without aki. Okay. Constraints. Jacobian matrix. So what we do is that we're comparing the constraints. This time I'm cutting the corners, so I'm going to simply, set the constraint for this one here, like here. And then I'm going to set these to be equal to 0 because it's a revolute joint. And the revolute joint is located in the origin of the global coordinate system. And then I'm going to take a look at this revolute joint that is located here. Let me change the color. This one. So I'm going to travel here like this and like this. I'm going to set these two notations to be equal. That's going to give me two additional constraints. Constraints 3 and 4. And then there's a primitive joint. where the motion in a global y direction is constrained, meaning that this one here is constrained. This is going to be my fifth constraint equation. Now Jacobian going to look like this. This is my constraint equations, which I'm differentiating with respect to my variables, which are Rx1 corresponding to the first body, the first body, and the same for second body. This is how the Jacobian reads. Then my next one is quadratic velocity, the externally applied forces. I have here pin force and the gravity force. Gravity is applying here and here. They are located in such that they're always in the origin of the body reference coordinate system. So when I compute the coordinates, it's going to be like this, and the mapping matrix becomes to be very, very simple. This is related to first body. This one, it's going to be a vector of 3 components. The same for second body, but this time it's going to be x component and y component, like showing here. Okay? When I'm putting these vectors together, this is how it reads. Okay? Then quadratic velocity vector, I don't need to worry about that because how the body reference coordinate system is located at. And then comes my QC vector. QC vector, I'm going to take my Jacobian, multiply that with the velocity. It's going to give me the vector of 5 components that will be differentiated with respect to my generalized coordinates, give me the matrix, and then that finally is multiplied by velocity, and my final assembly is getting to be so big, matrices, that I'm unable to put it in a writing, but that's it. And the response was something we looked a little while back, so the response was like, where is it? Hidden here. Oh, here. Like this. Okay, let me make it more clear. Like this. Fantastic. Absolutely fantastic. You like it? Well, you don't like that. So what's the big problem? So it goes to, okay, because, my computer is so fast. So let me run it one more time. So it's going to be like this. Nice. You like it? So you guys don't like this. Is something off? You need to tell me, is there something, it's a big problem, or, this, just need to remind you this. This is a computer simulation, so it must be correct. Is this how it behaves in real life? Is this, this is a mechanism you see in your car. Is this the way that the cranks up and the connection rod is behaving? No. Why not? You're right. It's not the way it behaves in reality. We have a big problem. We have a big problem because look at this. This point here is supposed to be here. So this system is broken. It is broken. Okay, this comes with 2 major lessons to you. Computer simulation could be correct, not necessarily. This is a good example when it is not correct. This is not correct because what we do here is that we are making pretty serious integration error. And the error comes from the fact that the constraints are taken into account in acceleration level only. Because remember how I introduced the constraints of my equation was the constraints were differentiated twice with respect to time. So it's meaning acceleration level. And when I come down from acceleration to velocity, I always introduce some amount of integration errors. When I come down from position, I'm going to make another set of integration errors. And this is what can happen. So the errors can accumulate. And when it accumulates, then the constraints are no longer fulfilled. There are tricks to avoid it. But this time what I'm going to do is that Oh, this is so small font that I might not be able to see this so well, but let's see. This is my my file. I'm gonna correct my settings such that it's gonna be a little bit of tighter tolerance. The tolerance is very, very small at the moment. So I'm gonna introduce the tolerance to be a little better. I mean, it was a very big tolerance, so I'm gonna make it smaller. So let's see if I can make any better simulation here. Okay? Better. So was it you that said that you are not happy with the response? Okay, you're gonna get the stomach aches because that's the worth of another cup of coffee. So you others, you need to come and help because your friend is drinking all the coffee here, and he's not. He's soon he needs to get the medical attention because of that. Too much coffee. Okay, 2 big lessons. You have to be very skeptical whatever comes out of from the computers. Another thing that you need to be very, very skeptical is your professor. If your professor is saying, okay, look at it, this is how the mechanism have to perform, you need to be at one say, I don't think so. I don't think so. It's not easy. Not easy at all. And I know that it is the hardest thing to do, but it's your responsibility because it's your responsibility. Not just this class, but other classes as well. You need to be the one that is giving these doubts. I'm not sure. Is this really the case? I don't know. Is it really that's how it behaves? Now, we will get back to this problem. We just look at a week from now. But right now, we need to go because we're going to have this question and answering session getting started in, in 16 minutes. So you guys go back home if you can. I'm going to see you soon. I'm going to take my stuff and go to my office. And like I mentioned earlier, it's going to be 45 minutes only because I need to be back home, family-related matters. Okay, guys, see you next week. It's going to be the final conclusion week from now. So take it easy and see you around. Oh, what about the in-class quiz? This one. Oh, okay, 100%.
Yes. Oh. Again, 1% was.
Okay, all right, now I'm going to close this one. Hold on, I'm going to close the recording.